Hey, welcome. Today I want to begin with a question. The question is, which stream that you can see in the pictures below has less resistance represented by less rocks and rapids? So what do you think? Well, the stream on the left seems to have less rocks and rapids and less interaction with the water and the rocks in general. Like on the right, it seems to be much more of a rough river situation. So if all things are perfectly equal, now these aren't perfectly equal, but let's imagine that they are, that the slope is exactly the same for both of these rivers, and that the only difference is that you have more rocks on the right-hand side. My question is, which river do you think would flow faster? Well, the river on the left would flow faster, right? All things being equal, if there is less resistance to the current because there are less rocks, then that water will flow downhill faster. Now, why are we talking about streams and rivers? And that's because these concepts apply almost perfectly as an analogy over to these ideas that we're going to be talking about today, dealing with Ohm's law and resistance. So maybe you are a physics student, or maybe you're an AP physics student getting some background, or a physical science student. In any case, what we need to talk about today with Ohm's law and resistance has a lot of water or river type analogies, as does a lot of circuit concepts in general. So we're at the tail end of an electricity unit, you could say, or sort of beginning a circuits unit, however you want to look at it. All right, so actually the current in a circuit is going to depend on majorly a couple things. There are other minor things too that we could bring up, but two major concepts, two major things that cause the current to be greater or lesser, the flow of charge or water, you could say, to be greater or lesser. So one of the things that the flow of a current of water would depend on would be the height drop. So if you take a look over here, let's imagine from this being our initial position to this being our final position, there's quite a significant height drop here. It's not really a waterfall, but there is a big drop in elevation, which means that the river is going to flow faster than if it wasn't as great of a drop in elevation, right? Whereas over here, this is significantly less in terms of its height drop, so as a result, its current is going to be significantly less as well. So definitely the difference in the potential energy from the initial position to the final position over here makes a big difference. And the second thing that really impacts the current in a circuit is going to be the amount of resistance in the circuit. So you could ask, does the stream have a lot of rocks or not many rocks? Because that does impact things. So generally speaking, the more resistance the stream has as it flows, the less fast the flow is going to be, right? And that is exactly the same concept that applies for electricity and the basis for circuits that we're starting to talk about. So if we're going to define resistance, we're going to say resistance is the ratio of the potential difference across a conductor to the current it carries. So this is what we mean by resistance right here. And this represents, in an analogous term, the potential difference between the initial position and the final position. You can think of it almost like the change in height per unit mass, you could say. And if that's a hard concept to grasp, it is. I'm convinced that potential difference is the hardest concept to truly grasp in all of the second semester of physics. And I've done a screencast to help you to understand what I mean by potential difference. I'll put a link to that in the upper right now. All right, well, we could rearrange this because this is kind of a definition of what we mean by resistance. We could rearrange this, though, and get one of the most famous equations in all of physics and one of the most important as well. This is called Ohm's law, and Ohm's law is going to help us to figure out how circuits are working and relate potential difference with current and resistance in different parts of the circuit or for the entire circuit altogether. All right, so just to talk a little bit more about Ohm's law, here it is again. Here is what these concepts mean. So delta V is the potential difference measured in volts. I is the current measured in amps, and R is the resistance measured in ohms. And in analogous terms, we're going to say that rocks represent resistance, and height difference or height drop represents the delta V or potential difference. And the current or flow of water represents electrical current. So I will come back to these concepts throughout our unit in circuits and as we finish up electricity, but just know that there are good analogies that can be made between water analogies and circuit realities. Alright, and so what I would like to quickly do is just use Ohm's law to solve a simple example problem. So it says an LED light bulb I bought uses only this amount of power, so 0.707 amps of power, across a normal household circuit potential difference of 120 volts. What is the resistance of the light bulb? So we have this equation we want to isolate for R, right? So we're going to go ahead and isolate for R. Then we're ready to plug in our numbers. We go ahead and do so, and we end up with 170 ohms of resistance for that part of the circuit for the light bulb. Alright, and now that we've done an example problem, I want to talk briefly about a couple different things that resistance depends on. So you have lesser resistances or greater resistances, and you can compare the factors here. So just take a moment to pause and think about this. So generally speaking, if you're talking about wires as resistors or resistors in general, like charge flows across the surface of a conductor, like copper wiring for instance, and if the length is greater, there's going to be a greater resistance. Or if the wire is thinner, all things being equal, there's going to be a greater resistance as well. Or if you pick different materials, like aluminum would have a greater resistance than copper. Or if you look at temperature, you would say a higher temperature conductor wouldn't conduct electricity as well. There would be a greater resistance than a lower temperature conductor. Part of the reason for that is the particles are bouncing around at a higher temperature. Even with the solid, those particles have a higher kinetic energy. They're vibrating in place at a higher speed, and as a result you have charge on the outside of the conductors that are trying to bounce along. Because those solid atoms are vibrating with more energy, it's harder for those electrons to move, at least for the electrons to move in a net effect. They're bouncing over atoms that are vibrating more consistently and more violently, so it's harder for them to move over the vibrating solid atoms of the copper or the other conductor in a net certain direction, and they move more slowly. There's a greater resistance. Alright, and moving ahead, I just want to say that there are a lot of smart people that are working on these problems. Because if you think about electrical power transmission over great distances, there is a lot of energy that's just lost because of resistance, and that energy leaving the system as heat or sound or a random noise of energy, you could say. So the more we can reduce that loss of energy, the less energy we have to produce. One of the things that's also worth mentioning is there's a lot of good research being done. So everything I've said so far with Ohm's law applies to a lot of materials, but it doesn't apply to all materials. Some materials are what's called non-ohmic. And what that means is they don't follow Ohm's law. They kind of do their own thing. And some special materials, for instance, if you cool them down to a very cold temperature, their resistance drops to 0. That's very important, because if we can figure out the secrets of what it takes to have something where its resistance of this conductor drops to 0, we call those things superconductors, by the way. If we can figure out the secrets of superconductors, then we could transmit power with no electrical power loss, without losing energy, so to speak. And that would be amazing, because it would save a ton of energy and help us to not have to waste energy in the process. In any case, that's a quick overview of resistance and Ohm's law. I'm going to be doing a lot more screencasts in this unit and in other units. If you have any comments down below, please let me know, and I hope you all have a great day. Take care.